So let's start. Thanks everyone for coming, despite some obstacles. So today we're happy to welcome José Dolz from ÉTS Montréal, who is a recent professor of laboratory mixed Central Superior. He's going to talk about efficient and robust adaptation of visual language models.
Okay. So yeah, thanks for this invitation. Actually, it came, I'm sitting prof at Central Superior here at the Mixed Laboratory. I'm working in ÉTS Montreal since 2018. Okay, and today I'm going to talk about a topic that I think is very common today. Visual language models. I think everybody is today aware of this kind of disruption in the field. Okay, so my goal today is to talk about how we can use these models for efficient adaptation and how we can have like a confident predictions of this model, which is something very important in real practice. So before that, I want to talk about my research interest so that you can know me a little bit more. I have been working since the last 15 years in computer vision, basically like standard tasks like natural imaging or medical imaging. I started with a more classical method like a conditional random fields, sift and sort features. At some point, at 2012, 2013, I started doing some kind of AI. So at that time was like neural networks, SVMs. Right after I started to work also in convolutional neural networks. So this has been the main core of my research in the last 12, 14 years. And today, there are two main topics that actually annoy me a little bit, okay? We can have these very powerful foundation models or very powerful models like convolutional neural networks, transformers, whatever. We can have like also very powerful computational resources like GPUs, and then we have a lot of data. We put all this together and it works, right? The problem is that in some settings, in some scenarios, we cannot actually have this access to that large amount of labeled data. For example, if you go to the medical field, okay, good luck to go to the doctors. I'll tell them, okay, I need 1,000 scans, like 3D scans, fully labeled. Okay, so that's unfeasible. So one of the main goals of my research is how we can train these models in an efficient manner. Okay, meaning that how we can use less supervision to train like high-performing models. And all this includes, for example, semi-supervised learning, weakly supervised learning. I think it's also a few shot, etc. So let's say let's say I'm from Montreal, we get some images for doing autonomous driving. Okay, we train the model. The model is super powerful. And then we deploy this model in the winter. In Montreal, it's not the south of snow in the winter. So this model doesn't work at all. So one nice solution could be to get new images from the new domain. So from Montreal in winter, get all these annotations and retrain the model. Okay, but that's unfeasible. So how we can transfer all this knowledge, how we can leverage all this, I would say, few information from a new domain, new class, etc. Okay, to adapt the model for new tasks. And the second question is, how we can actually deploy reliable models. So let's say when we talk about the uncertainty, we want to deploy models that they are robust or they are high performing in the sense that they give good, I would say, good predictions for the true class, but also we want them to be confident. So we want to, when they say, I'm sure of this, it's actually correct. And when they say, I'm not sure about that, it's because it's something maybe out of distribution sample, something which is very unknown. And the problem today is that when we have these high performing models, this is not the case. So even ResNet, which is, let's say, 99% in some of the datasets, when you look at the confidence, they are doing mistakes, but still it thinks it's very confident, it's doing good predictions. And we want to avoid that. I will show you one example that is very clear why we want to avoid all that. So having said that, my goal today is to talk about 3 recent papers we're doing in my group. Okay, if we have time and then during the post, etc., we can talk about maybe these 4 topics, but my main goal is to talk about these 3 recent works we are doing. So the first one, how we can adapt efficiently these click foundation models. Okay, so how we can get in a future scenario and adapt the models efficiently. The second part is how once we have this model adapted, how we can measure the uncertainty of the prediction so that we can improve what we call the calibration. Okay, and the third part is more about conformal prediction, which is a statistical framework for improving about the uncertainties. That's going to be the 3 main points of this talk. So I guess everybody knows today what's a foundation model, especially visual language models. Okay, a clip is a prominent example of that. In case you don't know it, I'm going to go like a quick overview of that. So the idea is that we may have like a huge kind of labeled data sets where we may have images like this, we might have the corresponding text. So for example, we have this image and we can say, this is an image of a dog. Okay, that will be the text associated with the image. We have one image encoder, which is gonna project all the input images to a feature space. So it's gonna have the embedding for each of the images. At the same time, we are gonna have a text encoder. This text encoder is gonna do the same for the text. So we are gonna have embeddings for each of the different classes, each of the different descriptions of the image. So the main goal or the main idea is that we want to have that the representation for the image and the representation of the text that is associated with that image is the highest similarity, right? Because they describe the same thing in different ways. One is an image, one is a text, but they are describing the same object, the same instance. So you want that the similarity of those two guys is the same. And imagine that then maybe the second picture is a shark. So of course, if we have here the description of this image of a dog, and then the second image is a shark, we want that the similarity between these two is minimal because they are not representing the same object. That's the basic idea of CLIP, okay, of almost any vision language model. How we do that? Okay, these features are L2 normalized. So meaning that if we want to compute the cosine similarity, we just do the dot product, okay, because they are L2 normalized. So here, there's going to be the dot product between the image and the representation, okay, the text representation. So we want to do all these cosine similarities, and once we have that, we compute the softmax. Okay, we want to bound it between 0 and 1. This is what we do, for example, in the prediction when we have the logits. So you want to have the softmax probabilities, so they are normalized here. We do the same across the text and all the different images. So now we have the softmax or the predictions normalized across one of the text and all the images. And then the way of training that against is what we want is that one image or one representation of the image has the highest similarity with the corresponding text pair. Okay, the ground truth is the diagonal. Okay, it's suboptimal. Okay, there are things to improve, but this is the first model that we're doing that. So let's say in this case, we have the diagonal. That's going to be the ground truth. So we want that the text encoder and the image encoder are trained in such a way that the similarities between the embeddings of the images and the corresponding embedding for the text, they are maximal. That's the way it's trained. And once we have that, we can do that, for example, with cross entropy. We do the cross entropy for the two things, from image to all the text, and from each text to all the images. And that's the way CLIP is trained. Okay? There's not something we did. This is just an introduction of this prominent model for visual language models. The beauty about that, and I think this is why has been a revolution, okay, of these models in the field, is that they allow zero-shot performance. What does zero-shot performance means? Now, once the model is trained, since it's able to encode the representation, the semantics from a text, we are now able to say, okay, now I want to create a dictionary, okay, of new concepts, new classes that weren't used for training. For example, let's say we train the model based on dogs, cats, and sharks, and now we have an image that we want to classify, and we say, okay, it might be a whale, or it might be a fisherman, or it might be whatever class you want, okay, a new class that was never seen in training. What we are going to do is that we are going to encode the representation of that semantics for that text. We are going to have different embeddings, and we are going to compute the dot product, okay? And at the end, what we are going to do, we are going to have the one with the highest similarity, and that's going to be the predicted class, okay? That's a main difference compared to a standard CNNs. When we have the head of the classifier, that's a fixed size. We cannot change that because if we change, we include a new class or we include a new concept, we need also to change the weights, and we need to retrain it. Here, we don't need that. Why? Because ideally, ideally, the text encoder and the image encoder will train a huge amount of data, and the text encoder is able to capture a different semantics for different classes. So like that, we can actually do the predictions in a zero-shot manner, okay, without having seen any sample from a new class we want to classify. Okay, and then this is what we predict. Basically, again, we have the dot product, we have the softmax, and we get the one with the highest probability. Now, the question is that, or the question we were asking at some point, okay, or we are all people working on this topic, deciding is that how we can go beyond that. Once we have CLIP, what else we can do to improve the performance or to do new things with that? Again, one of my things or one of my interests is how we can do that, or how we can do that in a very efficient way. For example, in a few shot. What few shot means is that we have a superset, okay, where we have images and the labels, okay, but only for a few samples per class. Let's say if I have like ImageNet is 1,000 classes, and we want to have like a 5-shot scenario, we are going to have 5 times 1,000. Okay, so that means that we are going to work in a few shot setting. Then very few samples for each new class we want to adapt. So one strategy is we have the text encoder, we have the image encoder, we have an image, and we have a text. So one strategy is to use the adapters. So in this case, we basically can put a few set or a small set of learnable parameters on top of the pre-trained frozen encoder. Okay, this can be either as a linear probing. I will show you later what linear probing means, or that can be something inside the network. So we can go inside each layer. We can include a few parameters, like for example, LoRa, like low rank approximations or similar techniques. And by doing that with a few parameters, we can adapt the model with a few samples. So that's one option, one strategy. And then we also have prompt learning. So in this case, the image encoder remains still frozen. The text encoder remains also frozen. And the only thing we change is the input on the text. So we can optimize the input such that the representations can be closer. Okay. The problem is, for me, is twofold. Okay. The first problem is this. So when we look at the timing, so at the adaptation time, this is for ImageNet and in Fusion. So we have these techniques which are prompt learning. They take like from 4 to 20 hours. Okay. Still, when we talk about efficiency, for me, it's far from being efficient. Not only the label space, okay, but also in the training space. So it's not very efficient in terms of computation. And then when you look at adapters, they are way faster. Okay. So that's one benefit of using adapters. Okay. The second one is that if we want to do adapters, if we do like a linear probing, so we put only a classification layer in addition to the model, this model becomes frozen. So this is like a black box. Okay, we don't need to see what's inside the model. We just get the features, we put something on top, and then we can modify it. In this case, even though you change just a small set of parameters, which is the input, you still need to do backprop. You still need to go through the network, okay, and modify this. So if you have some privacy concerns, that's also a drawback, a limitation from prompt learning. And the third thing, okay, it's true, but actually there are 3 things, is that when you check, let's say the model is optimized, and you check what was learned in the input prompt, I don't know if you have bought a furniture in IKEA, okay? In IKEA, you don't have vowels. When you say the name of the furniture, there is no vowels. There is no way we can pronounce that. It's something similar, so that makes no sense at all. Could be NV, X, T, whatever. So it doesn't make any sense what is learned. It might be optimal for the content of the image, but that doesn't make any sense. So that's why, from my perspective, okay, what we are doing, we just ignore, okay, or we are not trying to go through the prompt learning. We just go through the adaptation techniques here, okay? So some preliminaries for adaptation. I was talking about linear probing. What does linear probing means? So we have the clip encoder. So this is the vision encoder, which is frozen. So we don't change the parameters at all. Once we get this from GitHub, from any, Hanging Faces, whatever repository, we get the visual encoder, and this gets frozen. We include an MLP, like one single layer, okay, for a classifier. We have K classes, we have K output neurons, and then we have the weights here. This is the only thing we train in our probing. So we get the features which are normalized here. We train this. An important thing to keep in mind is that if you get these 3 or these n weights that go to the class 1, if you take these values for the weight and you put it in a vector, that's a prototype. Could be a prototype that represents that class in a feature space. Okay, with the same for the second class. So this weight, and this weight, each of these values you put it in a vector, and that's a prototype. Okay, for the second class, and so on. So this is basically in our probing. And then once you get the logits, okay, because you do W times V being the visual features from a text and from a visual encoder, you might get the logits. You put the logits in the softmax, okay, and then you get the probability for that class, okay, for each of the classes. That value you put it in the cross entropy. This is the white hat is the predicted probability, and y is the ground truth that you had in your superset. And then you train, you adapt the model. That's I would say, I think it's the naivest way to do adaptation from foundation models like VLM with Fusion. there is some problem though. Okay, the problem is that again, we are adapting the model with few shots. And when you think about few shots, think about the case of one shot. So how one shot can be representative for a huge testing data. It might be close, right? I mean, you have a tiger, you see how a tiger looks like, but maybe this image is not representative for the rest of the images for tigers. So the problem is that if we start with the zero-shot prototypes, that's the prototypes coming from the text embedding. So you get the text embeddings, okay? Those could be a prototype in the embedding space, the initial point. You want this model, you want this guy to adapt with the few shots, okay? But once you adapt it, you want that the new model, which is moved in the feature space, is able to generalize to any kind of image for that class. And also with domain shift. Again, it may happen and you want to classify a tiger in India, okay? And then you may have a tiger in a zoo, and there might be the environment could be different. There could be even a domain shift, or even might have a tiger in the day for the few shot, and then in testing you might have tigers in the night. So it's also a domain shift. The problem is that if you adapt with a few shots, you might go very far away from the initial embedding, okay? And that means that once you want to generalize, you won't be able to do it. So what you ideally want is you want to keep close from the initial prototype. So you want to constrain your search space for going from the initial prototype to the adapted model, okay? And what we found is that most of the state of the art at that time, and that's from last year, but maybe papers from 2022, 2023, they were doing this by changing the learning rate or some proxies that approximate the learning rate, okay? Which is kind of okay. The problem is that those were dataset dependent. So each time you have a new dataset, you need to fine tune that value, that lambda, or that proxy for keeping the prototypes close. And the things that you are not working in few shots, but if you want to do like fine tuning for each time you have a new dataset, that's not very efficient also, right? And the second problem we found is that some of the papers, I'm talking about even papers at CVPR, iClear, etc., they are fine-tuning this value on the test set. And of course, this is undisclosed, okay? And you can find this in the code actually. And we are not the only ones pointing to this issue. So with that, that's something wrong, right? So when you have the test set, you're working in few shots, but you use the test set to find the hyperparameters. That's something unrealistic, right? So what we thought is that, or we actually tried to do something like very, I would say, diligent evaluation, like empirical evaluation. So what we did is that we compare, so these numbers are the difference compared to a simple linear probing method. So we have the linear probing that I showed you before, okay? So how is the performance of the method if we train, or if we fix the hyperparameters based on this dataset, and we test in all these different datasets? Of course, when you test or you fine tune and you test on the same dataset, it's not bad. But when you change and you keep fix all the hyperparameters, the models don't work at all. And there's something you want to avoid. Let's say each time you have a new one, you need to fine tune. That's not very, very efficient, okay? So that was our motivation for doing this work, okay? So what we thought is that, okay, let's keep it simple in the meaning that let's try to do something that doesn't require very complex architectures, you know. I don't know if you know transformers. Sometimes you have the transformers, they start to do like bidirectional things here, so many, I wouldn't say weird things, but things start to get complex. So we wanted to avoid this kind of complexity. So we wanted to do something simple. So we kept the linear probing idea. So we want to optimize only the parameters in the last layer, okay? If we do that only, so we only minimize the cross entropy based on the predictions from W is the last layer, okay? What it might happen is that we might overfit to the official samples, right? So we are far from the ideal point. So we want to avoid that. So at the same time, we want to adapt, but we want to avoid to be very firm. So one simple idea is to use a constraint. So we can say, minimize this main function such that the new values, the new W per class, are close to the initial prototype from the text. I don't know if you know about context optimization, about the unconstrained optimization, you know, that's something related to that. So the idea is that we can keep these two different objectives. Again, adapting based on the cross entropy for the few shots, but at the same time, this constraint is going to try to keep close the new solution to the original one. Okay, and by that, we can try to avoid this problem. And now how we can do that? How we can integrate this constraint during optimization of the training. So actually a constraint, a very simple way, okay, to convert a constraint of problem into an unconstrained problem is to use penalties. So we can use a penalty, we can put this guy, so the text prototypes, we can move it to the left with a minus sign. And this can be like a L2, right? Like a L2 penalty. So it becomes this condition here becomes this full learning objective. Again, we minimize the cross entropy of all the set samples. And here we want to keep the new weights for each class close to the initial prototypes. And then we have a lambda value, which is going to control, let's say for each of the classes, it's going to control how much you can deviate from that. So the meaning of this is that if you go very far away for T, let's say for class 0, if you go very far away from this initial prototype, you are going to have like a high value, so you are going to penalize that. If you are very close, you will have like a lower value, you will penalize less. But still we have a problem. So which can be the problem here? But we have lambda k depending on the number of classes. If you have ImageNet, you have 1,000 classes, good luck trying to fine tune this. If you do your PhD on that, you can spend the full PhD just tuning the lambda values. So one thing we use for this, it's true, okay, you can spend the full PhD just doing that. So we initialize that based on the performance on the superset. It's a good proxy for initialization, that's fine, okay? The key point here is that for optimizing this as we move in the training, we use augmenting multipliers of Lagrange. Well, Lagrange multipliers, okay, I think I mixed French with English. You have the augmented Lagrange of multipliers, okay? That's a well-known knowledge, well-established knowledge in convex optimization, okay? And it's something very simple, even though it looks scary, it's something very simple. So the main idea is that, so we start with this initial function with the penalties, and we convert it to an augmented Lagrange multipliers. So we have this penalty function, typically it's a PHR function, which shows to be very powerful for these settings. We can use some other, but we just decided to use this one. So the main idea is that here you put the penalty, okay? You have rho is a value which is going to control how much you can change the multiplier after each iteration. And this is the multiplier that now you are going to learn. So you go from learning only W, again, W is the weights of the last layer, to learn W, but also lambda. So you forget about fine-tuning lambda, and it can be done automatically. How this is done, okay? So in the first step, so you have like 2 steps that you need to repeat multiple times. In the first step, you optimize W with a standard stochastic gradient descent, okay, with lambda and rho fixed. So you have the initial value of rho and lambda. You try to see how you can fit W to actually minimize the loss function here. Okay, or in this case, you can put it here. Once you have that, once you have found W, you fix W, and you go to find lambda and rho. So you get the derivative of the P function that I showed you before. Okay, and then you put with W being fixed, because now you learn it, you go to see how much you satisfy or not the constraint. So for each class, you see, okay, for this W, I'm very far from the constraint. If you are, you penalize more. So you increase more the value of lambda. If you are very close to the constraint, you decrease the value of lambda. And by that strategy, you can do that iteratively in an automatic manner. So you remove this need for doing fine-tuning of lambda, and you can accommodate n number of classes and being very large. Okay, again, we even try in ImageNet. ImageNet is 1,000 classes. Okay, and by doing all this, to my eye, simple strategy, okay, we can have something like this, which shows that that's our method, that if you include this simple constraint on the training, on the adaptation, you are independent to the dataset you use for training, and you actually improve the performance a lot compared to the initial models, state of the art in that spot. I'm not very fan of going to specific numbers, so I will show you basically the trends in this. And a striking thing, okay, very surprising somehow, is that here we have I data. That means the support and the test sets are in between the same distribution. Okay, so there's no change in the domain shift. But here OD means we adapt with one support set, okay, which is drawn from distribution A, and the test samples are drawn from distribution B. So there's a distributional shift between the 2 different distributions of data. And this is very surprising. So if we use VAT, which is a poor for method, a poor for upper, or poor for model, sorry, none of the state of the art improve the zero-shot performance. Again, zero-shot is from the text. There's not even images in there. So if you take the prototypes based on the semantics of the text, none of the state of the art, again, in top conferences, not only doesn't improve the baseline, it decreases substantially. Look at this guy. It's like 20 points less. And for me, that's tricky. And that shows that I think it's recording, so I shouldn't be saying very bad things. But this shows that we need to take care of, sometimes papers on the literature, okay? Because sometimes they are doing some things that get undisclosed, and sometimes you may find these surprising observations, okay? So that's one thing we observe here. And by applying our method, we are not improving, for example, in this case, that much. But again, at least we don't need any hyperparameter tuning, okay? And still it's improving over the simple baseline, especially for OD. When you have like a domain shift compared to the superset. So it doesn't depend that much on the superset anymore. Also, the method is very efficient. Again, it's only tuning or tuning. You need to learn the W parameter, which is the linear layer on top of the features. So of course, it's very efficient. It's very fast. Okay, especially compared to other models. While you get something which is most performant. So if you want to look at this plot, ideally you want your method to be in here. So the highest accuracy with the lowest computational time. So we are close to that. Okay. And this, of course, can be extended. Okay, that's something which is now under review. So here what we can do is, one observation is that in that case, in the previous case, T is fixed. So the text embeddings, those are fixed anchors, okay, for having the representation of the different classes. But you can move that as you fine-tune your feature space. So you are changing the structure of the manifold space, right? So why not, if you improve that because you are learning something more, let's say, complex, why not you can also move your text embeddings, okay? So we found like a very simple thing, like we have a Q function which is based on some accuracy, that if we improve the accuracy for the new weights, we can actually update the prototype. If we don't update, if we don't improve over the previous set of points, the previous set of weights, we don't improve, we keep it fixed. Why? Because if we are bad, why we are going to trust this model to go away, basically. And by doing this small trick, or this small change, we can improve also over all these methods for medical imaging. So even the previous method is CLAP, the one I showed you before, with the fixed anchors. If you modify the anchors, you have like 2% improvements, more or less. So you can still improve that by doing these modifications, on the flat for the text embeddings. So that's one of the first works I wanted to show. So now we know, well, I hope you know how we can adapt the models, the foundation models like a VLM, in an efficient way, so few shots for ID and OD tasks. Okay. The next question is that how we can deploy these models in a way we can actually have confidence of the predictions. Why confidence is important in this area today? Deep learning, I don't know how many of you are working in sensitive areas like medical imaging, autonomous driving, etc. But I think this uncertainty quantification is very important for any kind of critical decision system. So let's try to motivate this, and I hope you are going to be convinced about what I'm doing makes sense. Okay, this is the motivation for a topic. Let's say you go to the hospital now. That you have some collaborator. You go to the hospital and you say, hey, Dr. Peter, okay, I have two networks. One network is giving me 99% of accuracy for detecting tumors. So I'm able to say a 99% of accuracy that this image contains a tumor. And I have a second network, which is giving me 92. Which one do you want? So what do you think he's going to say, Dr. Peter? I would say this one. I mean, it's 99%. Why you want something which is lower performing, right? But the problem is that he doesn't have the full picture, right? What if the same network, now I give that image, and it says, it's a tumor, 100% sure. 100% that is a tumor. And the network which was performing lower, it's saying, I don't know. I never saw something like that. I can do a prediction. This is actually what we want to deploy safe models. I think it's very trendy now, all this robustness, reliability, safe AI, all this, okay, it's just fancy words, okay? But at the end of the day, what we want is that we want to have a network that is working very well, okay? When it's doing good predictions, but when it's doing some mistakes, you can be aware of this mistake and say, okay, guy, I don't know, you know? An example I put always, and this I can say even if it's recording, I think all of us, we have someone in the family, typically like a brother-in-law or something like that, that is that guy, that he knows about everything. It doesn't matter the topic, you know, in the Christmas dinner, it doesn't matter what you ask, he knows about everything. So we want to avoid that. We don't like this guy, right? So this is something we want. And this why thing uncertainty is very important in training foundation, not only foundation, but also standard AI models. So I'm happy to show you how we can do that for VLMs. I have been working on this for the last 4 years. So I have working on CNNs, transformers, like early AI models, and now we are, because of the importance, you know, of the rise of VLMs, I think it's also very important to go there. So how we measure the uncertainty? There are many ways to measure that, but the standard way, or the baseline, is what we call expectation calibration error. What does that mean? So let's say we have this toy case. Okay, we have few samples for a binary case, and we have predictions for the first and for the second class. So you get the Rmax, okay, and then you know that this guy, the first one is having the highest probability, highest softmax. So the prediction is going to be 0. For this one is going to be 1, and so on. Okay, and then we have the predictive label and the true label. Okay, so I pass to the next slide. So assume that those are the softmax that gave the argmax. So now what we know is that we predicted class 0 with a probability of 78%. We predicted 1 with a probability of 64, so far so on. What we do now is that we do some bins to put all these guys in here. So typically we use more, okay, but we are going to use 5 bins, okay, equidistant bins from 0 to 02, 0 to 04 until 1. So how many samples lie in 002? In this binary case, 0. There's no way we can put someone here. So we start in 04. How many samples lie in between 04 and 06? 2 samples. So we put these 2 guys, 4 and 5, we put it here. Then we go from 06 to 08, so we have 4 guys, okay? This 763, and we have 3 points in the last one. That's the first thing we do. Now, we go over all the bins, okay? And we compute the distribution of the samples, so 2 samples out of 9 fall in the third lane and third bin. We compute the accuracy. So we know that this guy was a mistake because he predicted 1 and the growth rate was 0. And this guy was a good prediction, okay? So the accuracy is 50%. So we just make good predictions out of 2. And we do the difference between that. So for our model to be well calibrated, we want that the prediction, okay, is equal to the average of the softmaxes. So this is the accuracy, and this value is the average of the softmax. So that if a model says, I'm sure at 50% of this answer actually is 50%. Okay, whatever goes on top of that or goes under that is either overconfidence or underconfidence. And we want to avoid all that. So we repeat this for all the different bins, and we get a value. Okay, that's the EC. So what I want you to keep for the rest of the talk is that if we increase this value, we are worse in modeling the uncertainty. So we want this to approximate 0. Okay, so as a basic metric we use for that, there are many more, but the basic one we are using for calibration. So what we observe is that when we have this VLM, so we have clip, this is the zero-shot performance of clip. So giving a given accuracy, I think is somewhere there. So you look at the normal line here, that's accuracy for this model. And then we have, I told you before, we have adapters, like here. So this is one clip adapter. We have prompt learning, which is modifying the text input. And then we have what they call test time prompt tuning, which is a specific case where you have the model, you receive test data, but you don't have labels. You need to adapt the model in test time, but you don't have labels. So it's a little bit more complex than these two. What we observed is that, yeah, these 3 models, they improve the performance of zero-shot clip. But look at these things, especially these 2 guys. So they are decreasing a lot the calibration. So they are becoming better in terms of discrimination, but they are becoming more confident. Now, again, we want to avoid that. So the next question is that why this happens? This, I think, is the typical question we need to put to start a paper, to start a work, right? Why this is happening? Okay, let's try to understand the source, the underlying source of this problem. So what we observed is that, and that's a belief, even myself we had before, is that calibration comes with the logic norm. So as you increase the logic norm, you might have a model which is more confident, because as you increase the logic norm, ideally, because the belief that we have, as you increase the logic norm, you might have logics that become higher. So the largest values become larger and the lowest one become lowest and minus something. So when you have something like this and you compute the softmax, it's close to 1, right? The closer you are, or the more far away you are between the logics, when you compute the softmax, the closer you are to 1. And 1 means overconfident. You want to avoid 1 at all costs. And we observe that actually it's not the logic norm. So for these two cases, yeah, the logic norm decreased, but for these ones, either it kept the same or slightly increased. I think in this case, slightly increasing. But on the other hand, we observe that it's not the logic norm, but the logic range. So when you compute the range of the logics, so the maximum value for the logic and the minimum one, and you compute the differences, the absolute difference, that's the one which is playing a role in that. So we saw that in all the cases, the logic range is increasing. So first, for me, was kind of surprising, okay? Because we believed the logic norm was the cause of calibration, one of the causes for calibration. So having this in mind, we said, why not? We try to correct all that. So something very simple again. So we have an image, we get the frozen model of clip, we get the zero-shot prediction, even if it's a testing, we don't care, okay? We get the zero-shot prediction, and we get the logics, okay? Now what? We keep the largest and the lowest value. So for that image, the largest and the lowest value, we're going to keep it, okay? And then we adapt the model, either with the cross entropy, we have few shots, or the entropy, we do system adaptation, okay? Any kind of loss, we adapt the model, and once the model is adapted, we have this guy, this image, and we compute the new prediction. And then what we want to do is, in this case, the softmax is going to be higher because you have this guy with the rest, which is higher the difference. But then it's something so simple as saying, okay, we kept the range, the extremes of the range for these logics. Let's map it back. Okay, let's have the new ones, and we map it. In this case, we don't change the prediction because the Rmax doesn't change, okay? But we might change the different distributions of the softmaxes, and this can reduce the overconfidence. Now, let's say the intuitive idea of having this constraint, okay? And we thought about 3 different ways of doing that, okay? And surprisingly, the easiest one is the one that worked. The first way of doing that is that we have the standard cross entropy. So we go over all the supersets, over all the classes, then we have the softmax, and then these logics, we map, we renormalize the logics based on the mean and the max of the logic range before putting that in here in the softmax. And with that modification, we keep on training. The problem with that is that, yeah, once you have the logics, you can constrain the values, okay, because you map it. So in this case, once you map it, the max and the mean are going to be the ones that you computed before. The problem is that you put this in a loss function, that's going to have some gradients. And based on the predictions, you might change those values because the gradient is telling you, okay, the class 0 is incorrect, put it down, the class 1 is correct, so modify it. So yeah, it's making an effect, but it's not actually satisfying these constraints. So a second strategy we decided to use, or to evaluate, is to use explicit constraints. So we can have like these this inequality constraint can be decomposed in one inequality constraint that can be implemented with a ReLU function. And then you can have a second constraint, which can be implemented with a second ReLU function. So basically, whenever you are either lower than the zero-shot minimum or higher than the zero-shot maximum, you are going to put a penalty. Okay? And that's more principle. And to be honest, that was the one I wanted to work because, sometimes when you are doing some works and you are doing some missions, reviewers, they want some complex maths, they want something, and I was like, this is cool. This is going to work, okay? And then my student told me, okay, Jose, let's try a very simple baseline just to rule out some, simple things. So we basically got the prediction. We didn't change anything in training, so we got the prediction as it is. We map it to the zero shot margin values, okay? And we transform it. That's it. Post-processing, I don't know if you know temperature scaling. Temperature scaling, so temperature is a value you have, is a scalar you have in the logit. So you have softmax logit divided by t. With t, you can control the shape of the distribution. Okay, and typically that improves also the calibration, but you need to fine tune also t. Is dependent on many things, so it's kind of stangler. It's a mess. You can do that. But this is an automatic, unsupervised, adaptive, sample-wise, whatever you want to call it, temperature scaling. So you can adapt the distribution in an automatic manner. So surprisingly, look at that guy. That's the post-processing. It's giving the best performance. So it's keeping the performance, the discriminative one, compared to clip, because of course, you don't change the argmax, you only redistribute the different logits. But it decreases a lot the EC, the expected calibration error. So these two are somewhat working. Penalty one is typically giving the highest performance, it's improving the performance of the discrimination, of the classification of the different models. But this is not getting the same calibration error. So at some point, I was like, okay, cool. It wasn't the one I was expecting, but something simple like doing this post-processing was actually working very nicely. Okay, and that's cool because you don't need to retrain the model. You can have like a black box prediction. You just adapt it, you refine it or parameterize it, and then you have your better uncertainty estimation. That was for adapters. We apply the same for problem learning, and we observe the same trend. So this SAS, which is the post-processing, is actually giving typically, okay, the lowest performance. Well, in this case, I think problem was a little bit different, but still you can improve over these baseline models, which is the model without any kind of uncertainty quantification mechanism. Okay, so we have seen so far, I don't think we will go through the 4 points. We have seen the adaptation of VLNs. We have seen how we can evaluate, how we can model the uncertainty better, so how we can deliver more confident or more reliable models. The problem is that when we are doing this calibration, there is no guarantees we are doing things properly, okay? And to avoid that, we have conformal predictions. So I don't know, except Bada, which is one of my students, that he knows conformal predictions. I know the rest you know about conformal predictions. So this is very cool because it's a mathematical framework with guarantees of coverage. So what that means is that giving alpha is a value given by the user, okay? So this could be, for example, like typically we give like 10%. That means that with a 90%, so 1 minus alpha, like a 90% of probability. So the probability that the ground truth is inside the conformal set should be higher than 1 minus alpha. That's what conformal prediction means, okay? So I want to give a conformal set, which is a set of different potential classes. So at 90% of a marginal coverage, the good class, the ground truth class is going to be here. Okay, so it's not anymore just providing one simple class. It's giving a potential set of classes with a given probability. For doing that, well, the process for doing that is basically, I will go kind of quick on this. Okay, basically you have a calibration set. With this calibration set, you are going to first compute a non-conformity score, and a basic non-conformity score could be this. So you get the softmax of the ground truth class, not the predicted one, the ground truth class. You do 1 minus alpha, and that's going to give you the non-conformity score. You put the set of non-conformity scores for the calibration set here, okay? And this basically will tell you need to compute a quantile, okay? So you compute a quantile, which is sometimes it's like a 90%, 95% of all the different non-conformity scores. And with that, you compute your empirical conformity score for the calibration set. And then once you have the testing images, you basically you apply the conformal set, the conformal function over all the test images. And you see for that, for each of the classes, which is S. If S is lower than the non-conformity score of the calibration one you found here, you put it in the set. If it's higher, you don't put it in the set. Okay, that's it. That's conformal predictions. this comes with very strong assumptions. For example, you need to satisfy exchangeability between the calibration and testing samples. If you don't have that, that's going to be more complex, okay? There are some discussions we are having on this, what to do if we can just smooth some of these assumptions, but the basic thing, especially now to keep in mind, is that we are under strong assumptions, specifically the data exchangeability between the data calibration set and the testing set. So that's very cool. There have been many works on simple tasks like regression, like simple CNNs in Cypher 10, Cypher 100, all that. But there was nothing for VLMs. And again, I think given the importance of VLMs, the rise of papers in VLMs, we thought it was very important to also tackle this problem there. So let's say we are in the VLM setting, the VLM scenario. So we have the clip model, which is frozen. We have a calibrate, we have a few shot set, like the one I showed you in the first talk, in the first part of the talk. And then we have a test set. So what we can be tempted to do? I think given that, the first thing I would do, or the first thing we did, actually, that you fine-tune your model in the calibration set, which is the superset. Okay, so you adapt this model to the new distribution of data. And once you have that, you can use that calibration data to find your conformity score. Okay, the problem is that if you fine-tune the model and you bring it close to your calibration set, it's not data exchangeability. You are breaking this assumption because that few supports are not representative of the huge test data set. So once you are doing that, you break this assumption. And which is the implication of that? So if you break the assumption, so you break the exchangeability, your coverage decreases. Again, it's a mathematical framework, a very strong framework with theoretical guarantees. So the moment you don't follow the assumptions, it doesn't work. So we observed that we are doing that. So we first adapted the model, and then we use that same data set to calibrate. You break the data exchangeability, and the coverage decreases substantially. So what can be done, to improve all this? You can do many. I'm sure you can do many things. Okay, but one thing we thought at the time is that why not we put all that in a transductive setting? So transductive means we put all the data together, like clustering. Clustering typically is transductive, right? You have the k-means, okay, you know the k, you have all this data together, and you do prediction at once. So why not we put all this in a transductive setting, meaning that we put the calibration data set and the testing and label data set, okay, all together, and we try to see how we can leverage all this information together. So if you put this with a VLM, you have the visual encoders, so you have the embeddings for each of the images. You have a text encoder that is going to project all these prompts in text embeddings, and then you compute the similarity matrix, which again is but you have a transport that you have T is the matrix of all the vision features, or in this case is the text all the text features, and set is the one of all the vision features. You compute that similarity matrix, and you get something like that. Okay, a similarity matrix. Then the goal is that we can find how we can actually have like joint probabilities to maximize these similarities. So one strategy we decided to use is optimal transport, okay, for doing that. So optimal transport, I don't know if you know it, is basically a framework that can help you to move the mass of points. It might have different masses, and it's going to have like a cost. So when you have T, it's going to be the transport plan, and what you want is you want to minimize the cost of moving all the mass in this distribution to this one. So basically speaking, you want to transfer or you want to match two different distributions, okay? So this is what you typically do for optimal transport. So you want to maximize the trace of these guys here. So this is the S is the similarity matrix, Q is the transport, the transfer, so in this case, the label assignments, okay? And this is what you want to find. So all this is the polytope of the transportation cost, okay? Where you have here some constraints. Okay, for optimization, you need some constraints. If not, that will give only nice solutions. So this one is a sample conditional marginal distribution. That means that all the samples should equally receive all the mass. Okay, and this one is the label marginal distribution, meaning that the prediction should be uniform. Okay? You can have like a uniform distribution of the classes evenly to all the samples. What we observe is that, or what we thought is that why not, instead of having uniform, we know the labels of the calibration set. We still know it, right? Because we have labels here. Why not? We can replace this uniform distribution by the empirical marginal or label marginal we have in the calibration set. Like that, when we try to match the two distributions from the calibration to the test set, we are going to transfer some of the properties of the calibration set. Okay, so we replace M being uniform by M, the empirical observed label marginal. And then this problem can be solved with a synchron algorithm. So we can put here an entropic constraint. Okay, so we want to maximize also the entropy of the assignments, and we can use the synchron algorithm. It's very efficient. Okay, and you might find the label assignment, the soft label assignments very quickly. Okay. Once we have that, so once we have optimal Q established of the optimal Q, the optimal soft label assignments, we do conformal predictions, but based on Q star. Okay, not anymore in the predictions itself, or not anymore in what we had before, but in Q star. So we have the calibration set that we use to compute the non-conformity scores based on Q star. We compute the quantile. Okay, the quantile I showed you before. And now once we have the quantile, the good thing is that now these two guys, they have the same distribution. So we approach two different distributions. And actually in this case, it's working much better because we assume, or we can fit, or we can satisfy very, very well the distributions. So when we have a test, we go over the Q star, and then with that, we compute the conformal sets. Again, going quickly through the numbers, here you can see that compared to the baseline method, so for each of the different, those are lag, ups, wraps, are like the well-established non-conformity scores for the conformal literature. By applying this method to this conformal OT on top of them, we can improve like 3% for the top one score. Okay, so it's basically top one means you have the conformal set and you get only the highest probability. Okay, you can still satisfy the coverage. Okay, but very importantly, you can improve the efficiency. The efficiency in conformal prediction is the set size. Think about that. You have ImageNet, you have 1,000 classes. If you give one vector of 1,000 classes, of course, you get 100% accuracy. But you don't want that. You want to keep on improve the accuracy, at the same time minimize the size of the set, right? So you can see that in all the cases, you can also decrease, sometimes substantially, the set size given by the initial or the original method, okay? And then most importantly, I saw some of you were saying like this when I say synchron optimal transport, typically something which is very expensive, sometimes, okay? If you keep to the strict optimal transport conditions, you might have something which is more computationally expensive. But just to give you an intuition or the context, taking all the features takes around 4 minutes, okay? And this comes in any way. Whatever you apply after, just extracting the features gets around 4 minutes. Doing all OT, S assignments, and the inference for different methods doesn't even take 1 second. So what's 1 second on top of 4 minutes? Okay, so it's very efficient. So it doesn't add any kind of complexity, or is negligible. And then here you can see that you have different techniques to impose this kind of label marginal distribution, between the calibration set and the test set. Okay, this is doing this directly on the predictions. These are the state-of-the-art method, I think was CVPR 24, and then there's our method. Okay, some results to show we are good, something we need to show, right? So I think I'll end here. It's already a good almost 1 hour. So take home message, there are many here. Okay, one is that VLMs are becoming very popular. I think almost everybody knows today VLM, they want to do VLM, which is very nice. I think there are many opportunities there. So actually, I would say all what we have seen in standard networks, everything can be applied, almost everything can be applied now to VLMs. Let's say you go to the Fuchsia. Fuchsia was, with meta learning, it's something I have some, well, it's fine, okay. Meta learning was 2017. Now we can see it in VLMs. Uncertainty, I was working on uncertainty 2019, sorry. Now we can see it in VLMs. We're seeing semi-supervised. Now we see semi-supervised SAM, so I think it's very important to keep that these are new type of models. They are very powerful, but all the problems we had before, we have it now also, right? So I think that gives gives it, you want to stay in research, especially for PhD students or master students, there are many opportunities for adapting VLMs in many new scenarios. Again, it's very far from being solved, okay? And yeah, we always show that it's improving, but let's go to the real practice. So if you give a doctor, again, I'm working a lot with the medical domain, that's why I talk a lot about doctors, and you tell them, I have a VLM, it's SOTA, 45% accuracy. They're going to tell you, okay, come back in 10 years when you have 85. So yeah, we are improving over previous methods, but we are still far from being solved, okay, or being something usable sometimes. Then I think it's very important to not focus only on the classification, segmentation in the discriminative side, but also in the uncertainty quantification. I think a trade-off between both, I would say, both phases of the game, I think is very important for having safe, efficient, for having method that we can deploy in real practice, in real world. Okay, I've been talking here about classification only. Okay, but there are more than that. The segmentation, for example, segmentation is an extension, natural extension of classification, where you look at the neighbors. Not only the metrics, but also the methods used for calibration are focusing only on classification tasks, okay, and ignore or disregard all the information about the neighbors. So I think it's very important when you consider, for example, the metrics for calibration, or you consider methods for uncertainty quantification, you can take into account also what's happening around. Let's say for the same point, for the same pixel, okay, with the same intensity, you cannot have the same uncertainty. It depends on many things. It depends how many of the neighbors have the same intensity. Is this in the contour, or is this in the inner part of the object? So it depends. There are different scenarios, and I think those should be treated differently. Yeah, despite of the importance of the topic, you know, VLMs, more recently conformalization, there are not many works on that. I think calibration, which is previous to conformal, I think there were, when we published that paper last year, I think there were 4 papers before doing calibration of VLMs. Now already published, there might be 7, 8 papers. Okay, I'm talking about the top conferences. There might be some papers under the radar, but more or less like that. And conformal in VLMs, but there are 2, 3 papers maybe. Yeah. So they're not more than that. So again, it's very important. I think people know it's important, but still, we don't see much work on those spots. And for me, that's the $1 questions. Once we have all this conformalization, calibration, etc., how we can leverage all this for doing misclassification error. Okay, I think that's a very important question, because I know some of you are working in this topic. So basically, here what you want to do is, now I give you a prediction, tell me if it's wrong or not. Okay, if we have that, I mean, we have the how to say that, the holy grail, okay, for all that. We don't have that so far. What we have, there are some methods that they are based on the shape of the softmax. They compute some energies, they play with the Shannon entropy or the Renyi entropy, they play with all these information theoretic measures to establish whether some predictions could be good or not. The problem is that those assume you have very peaky distribution. Okay. The problem is that if you go to calibration, you are going to say the distribution of the softmax is going to be smooth. So you might have something like this. If you think out all in 0 or in 1, you are going to have something like this. And with this, applying all this method will not work. And that I know, because I have been trying that. So for me, this is one of the key questions that hasn't been solved so far. So if you are interested in some of these topics, I invite you to maybe investigate all this. So how we can have all these very fancy, very nice things. But once we have that, how we can deploy, how we can leverage all this to actually find misclassification error. And if we have something like this, this could be the door, you know, for putting all these methods, for example, in clinical routine, in safe application like autonomous driving or anomaly detection in industries or something like that. So with that, this is not my work only. Okay, I'm working a lot with my colleague, Professor Ismail Benai. Okay, he was my postdoc supervisor. Since then, we are working a lot together. And this is the work from 2 of my, 1 PhD, 1 postdoc student. Okay, we have many more works, but this only for these 2 spots. And then, you know, with funding, those guys are paying my students, so we have to put them in the talks.